Hey everyone, hope you're all doing well. This is Aditya from the Rakuten 6 Sense team, and in this webinar, I'll take you guys through some war room scenarios and how our cognitive AI solution can help you get through these scenarios in a very efficient manner. I'll show you those scenarios where alert storms are a big problem and where there are issues regarding application topology as well. So we'll show the current as is solution and what are the problems associated with it. And right after that, we'll go through the Cog AI solution and how it solves the issues in the current solutions and how it can change the landscape of observability as we know it today. So without any further ado, let's get started. All right. So in this slide, you can see that we're painting a classic war room scenario where one particular component has gone bad, which you can see on the left hand side of the screen. And that is leading into a storm of alerts. You can see that there are a couple of alerts on the load balancers, on the firewall, on the common network layer, which the applications, database, firewall, and load balancer are on. You can also see that there are many alerts on the applications or the services as well. And of course, finally, alerts on the database as well. So just one component going wrong can lead to a storm of alerts, and that can lead to a huge number of tickets for your SREs to have for them to have to sift through and solve and isolate the core issue of what is actually going wrong and where the problem is and how to fix it. Now, think of this. Each component of these will have, let's assume, 5 different KPIs to look out for. All in all, this will come up to about 50, if we're being positive, 50 different KPIs that SREs must constantly watch over many, many screens. And like we can see over here, in the event of the core component going wrong, nearly all of them will throw out alerts. And that's going to lead to a huge loss of time and productivity just to find the issue, let alone solve it. So, this is one example, and we will see more going forward. All right. So, in this, we're going to see the war room scenario and causes and the issues. So, now in all of our applications, there is some element of seasonality. You may have, say, an e-commerce solution or an e-commerce platform, and those have a lot of seasonality, right? For example, if there's a holiday like Diwali or say Christmas or a Black Friday sale, there's going to be a huge number of users which are going to log on to your platform. But in normal times, you're not going to have that spike. So when this seasonality occurs during, say, these peak times during the holiday season, you're gonna get a lot of false positives, and these false positives will actually be what you expect. But because you're not used to those highs of the holiday season, you're going to trigger them as false positives. Another result rather, of the false positives leads you to miss critical alerts. So, because of this storm of false positives, where things are actually going the way they should, but you're still getting alerts, you might actually miss something that's going wrong. And because of this storm of alerts, you're going to miss whatever's actually going wrong, if anything is going wrong in that case. Thirdly, the lack of correlation between domains leads to an alert storm. So if there are, say, two metrics which are either positively correlated or negatively correlated, you're not going to be able to see that correlation in traditional AI ops tools or observability tools. And because of that, you'll see an alert storm as well. For example, if the RAM usage is going up and the response time is going up with it, that's going to be normal. That can be made in just one alert. But instead of that, you're going to get 2 alerts, 3 alerts, 4 alerts, or how many other correlated alerts and metrics there are. And in the current solution, using only rules and topology leads to limited reactive root cause analysis. There's not a lot of AI in just using rules and topology. It's just following a rule which you have specified from your tribal knowledge, and you're going to be using that to get to the root cause. And that is one, very time consuming to set up, and two, doesn't account for much seasonality. So all of these come together to form the perfect storm. Because of this, the MTTR, the mean time to resolve issues, spikes up. There's almost zero predictive intelligence because you're only seeing what's going on in the moment. You're not necessarily predicting into the future. And because of that, there's a Chinese wall between devs, QA, and Nox, and DevOps, anyone who's involved in making and building the product. There'll be no communication between them, and isolating issues will take much, much longer. So here is one example of a problem that our Cog AI solution can solve. Here, there's been a change in the web application firewall file, or the WAF file, and some third party has found a loophole or some kind of backdoor in their web application firewall file. Because of this, they can exploit it, and they can start a DDoS attack, a distributed denial of service attack. That can lead to a whole storm of errors again over here. Your CPU load average time might increase, your system uptime may go down because it continuously crashes, your process CPU usage might increase, the memory used might increase, your server might start restarting more, the memory page falls per second might increase. A whole lot of alerts, which your war room will be looking out for, will start throwing out a storm of alerts. And you may not necessarily find the root cause of these alerts, right? Like over here, you won't necessarily be able to figure out that because a web application firewall file was changed, some configuration in it was changed, is the reason why this DDoS attack occurred and why all these metrics are shooting up, all these alerts are shooting up. So that's one issue where there's not necessarily something you can pinpoint and say this is the reason why your alerts have started shooting up. There's another example, and we'll see that in the next slide. Another example of the alert storm is related to the topology. And in this case, the source of the issue is not on the topology at all. For example, we have one service over here which is connected to, say, an AWS EBS storage. And that EBS storage, for some reason, maybe it's run out of storage, maybe it's run out of memory, maybe someone changed some configuration, maybe someone accidentally shut down. For some reason, that AWS EBS storage is not responding properly. And because of that, the service that's connected to it, or the services that are connected to it, will also not function properly. They also start throwing errors, and they'll potentially start affecting the applications and services and components that are connected to that service as well. And many tools can help us get till this point of where the service is and what the issue is on the service level. But the real cause will be some configuration or some problem in the AWS EBS storage, which we'll not be able to pinpoint with traditional solutions. It requires tribal knowledge, and there's a risk of very, very late root cause analysis with this. Establishing storage as an issue or as the root cause is actually quite hard because of this, because you never really know. You only know at the service level, not at the storage level. So because of these alert storms and these war room scenarios, you want your SRE and your site reliability team to be at their peak, to be able to solve the issue as well as possible. But these dashboards can get overwhelming. If you're getting 50 alerts every 5 minutes, you're not going to know where to look, and you definitely will have a very hard time figuring out what the actual root cause of the problem is if you're getting overwhelmed by alerts every minute. So, the current as is, there's a tightly coupled topology, and there's not much flexibility on that tightly coupled topology. In the previous slide, we saw the example of how an AWS EBS storage was not functioning properly, and as a result, the corresponding service connected to that also was not functioning properly. That would have thrown out a lot of alerts that may have impacted some of the other services which were connected to it, and those also would have thrown out a lot of alerts, resulting in yet another alert storm. That's one current issue of the current solution. The current solutions are also intense and they're only real time. You're only going to solve problems once you know that the problem is actually there. The current solutions also do not necessarily have cross domain correlation. So, say if there's a RAM issue in one service, or say the error rate is increasing in one service, and the response time is increasing in a corresponding service, you're not going to see that correlation in current as a solution. And because of that, there's missing correlation pieces, which can hugely assist you in finding the actual cause of a problem and any potential impact which that might have in the future. So that leads us into the reactive RCA, which current solutions provide. And because of this reactive RCA, because you're only solving problems once they come up, that's going to lead to a storm of alerts. Another issue is that alert mechanisms currently are derived from manual thresholds. You set a threshold, say, send me an alert every time my response time is above 1000 milliseconds, and then you get an alert in your email. There's no true automatic thresholding. Most solutions only take a short range of data from maybe 2 weeks past, and then they get an automatic threshold from that. Because of that, they don't really understand seasonal nonlinear metrics, and current solutions struggle with seasonal nonlinear metrics because of that. If you're seeing data from only say 2 weeks ago, and you're not remembering data which happened from maybe the last month or the last year or the last 5 years or the last 10 years, you're not going to cope very well. Your model is not going to cope very well with the seasonal metrics. So all of these problems, which are in our current as-is solution, can be solved by Cog AI. Now, how Cog AI solves all of these issues is it auto detects the root cause and it notifies you that this is the root cause of whatever issue that is in your application estate. It also detects anomalies and does almost instant RCA or root cause analysis. And it also automatically correlates metrics while seeing the metrics and getting them fed in live. So here, for example of how our Cog AI solution can help find anomalies which may not be flagged, we have an example of, say, a food delivery app's traffic on Friday, for example. You can see that the spikes start after 5 p.m. or close to 6 p.m. almost, and the traffic is rising. However, as the traffic rises, there are sharp, almost random dips in the traffic before it regains its normal trajectory. Now, in the normal current solution, those dips, those random dips, those sudden dips, they will not be flagged as anomalies because they're staying well below the threshold that has been set. But in cognitive AI, those anomalies will be flagged because even though they are, say, below your threshold for what you consider normal, that is still abnormal behavior. Your traffic, while rising, it normally would remain constant. It would follow the same trajectory. It's not going to seeming randomly dip out of nowhere, right? Cog AI will find these low traffic anomalies and it will tell you that something's going wrong, and it'll also lead you to the root cause of whatever is actually causing these dips. Maybe a load balancer is not configured properly or it keeps restarting, and that's why a lot of people lose the connection and the app traffic of the app reduces. So in this slide, we have a picture of the actual application. And as you can see, there are two correlated metrics over here. The first graph shows the listener in out traffic, and the second graph shows the concurrent slash maximum number of listeners on an Nginx web server. As you can see, the metrics are seemingly correlated, and when one rises, the other is expected to rise as well. So, in this scenario over here, being painted by the application, there is a sudden spike in load. Say it's an e commerce business, and there's a sudden spike in load. And there is also, because of there's a sudden spike in the number of listener in out traffic, there's expected to be a spike in the number of listeners on the Nginx web server as well. But that's not happening, as you can see in the second graph. The number of listeners on the Nginx web server is actually stuck at a constant 1,000. It's not rising as expected. It's not rising as high as it should, as it's correlated with the listener in out traffic. So that's a critical alarm because you're going to lose a lot of business because of this. You're having users who are trying to connect, but they're not able to because some configuration change was made on the Nginx web server. And because of that, you're going to lose out on a lot of business, you're going to lose a lot of revenue as well. So, very abnormal behavior is detected and flagged as a critical alarm, or what we call an anomaly in this. So, this usually happens when the forecast and the ground truth have a huge gap. In the second graph, you can see the blue line is the forecast and the orange line is the ground truth. So, what is actually happening? And there is a huge gap between them, which is when Cog AI throws out an alarm or a critical alarm. These require immediate attention, otherwise, you're going to lose out on a lot of business and there's a loss of revenue as well. Uh, in case this behavior was expected, however, you can always provide feedback to the model and say, yeah, this is a false negative. We expected it to happen. We wanted this to happen, and the model learns from that and retrains itself so that the next time it detects a potential similar scenario, it knows not to throw an anomaly and the user does not get bombarded with alerts. So the first thing we'll be looking at in the Cog AI solution is correlation. And here in correlation, we mean the correlation between metrics, either in the same domain or in different domains. So if say the RAM usage of a particular application is increasing, we can correlate that with the response time and say because the RAM usage is increasing, the service is becoming slower, and because of that, the response time of this service is also increasing. So when there is a change detected in say any configuration file, for example, in the web application firewall example shown earlier in the webinar, Cog AI detects that some change happened by looking at the logs. And when that change does occur, the entire engine is on high alert. It starts forming sequences of whatever happens with metrics and with events, and it stores those in its memory in case something goes wrong. So the next time some error happens now or some issue happens now, it shows you the predictive sequence of how it believes that that error originated or that issue originated, and it also can tell you the potential impact. It does this by learning from history and how and the seasonality and any feedback that the user provides. So whenever this happens, it can show you the predictive sequence of what it believes what went wrong with all of the correlated metrics and the correlated events, whether it be from the same domain or cross domain. And it can tell you the potential impact, again, from the same domain or cross domain. So over here, there was a change detected in the load balancer, and that led to a critical breach of the concurrent or maximum listeners. That's the scenario we saw earlier, where the number of listeners was not going up as high as it should. And because of that, the potential impact was finally an impact in the login service. So because the load balancer was not configured properly, before issues started arising fully or alert storms occurred, Cog AI tells you that the impact is detected in the login service, and that's what's going to get affected if this issue persists. A core differentiator of Cog AI is its sequencing. Now, sequencing is basically finding out the root cause and the potential impact, very similar to the correlation, and we'll explore that a bit more with an example. So, taking the same example of the change detected in the load balancer, which was in the logs, we finally figured out that the potential impact of that change, which was in the load balancer, will finally be seen in the login service. Your users will not be able to log in, or they'll have a hard time logging in, or the login service will not work at all. So, the root cause is automatically isolated intelligently with sequencing. So, what happens is when the engine is on high alert, it starts forming sequences of whatever is happening in that moment. And whatever the engine feels is relevant by looking at changes in metrics or looking at the correlated events, looking at whatever the engine feels is relevant, it starts to form sequences. And in the future, and it saves these sequences. So when in the future a similar thing happens, the engine can refer to all of these sequences and it can tell you the potential impact and the potential cause before any core issues start arising. So this can give you a vital 5 or 10 minute heads up before the war room scenario even starts, because the engine has learned from past scenarios and it knows what potentially can get impacted and what the potential root cause was earlier. It can send out a notification saying, hey, look, I detected this change in the load balancer. And the last time this happened, along with this breach in the Nginx web app, I saw that the login service was detected. So it can tell you 5-10 minutes that your login service might start going wrong. It might start throwing out alerts. And this can save you and your team a lot of time, a lot of energy, and a lot of money. And it's a problem that can be solved almost instantly before it even arises, in fact. So, how Cog AI starts to get triggered to be on high alert is in one situation when it detects a change in logs. Changes in logs can occur, say, when some configuration change has happened. And when this happens, the engine is on high alert and starts to perform its correlation duties and its sequencing duties as mentioned earlier. Looking at these changes, it can help find the cause of the problem which is going on now. And if any similar problems occur in the future, it can pinpoint to past events and say that this change is the reason why everything went wrong. So, in this example, the IP address of some server or some virtual machine was changed. It was edited. The network configuration was changed. And Cog AI intelligently detects these changes via logs. There's no extra configuration of the engine itself which is required. As long as you feed in the logs, the engine will find out that some configuration was changed in whatever capacity, and the engine goes on high alert. When it's on high alert, it starts forming sequences, starts correlating events and metrics, and it stores these so that in the future they can be used. And if any requirement is needed instantly, suppose some service goes wrong, it can pinpoint to this configuration change and isolate that as the root cause of the issue. So, in the example we saw earlier in this webinar, there was a storm of alerts. The CPU load time was shooting up, response time was shooting up, RAM usage was shooting up, and no one really can figure out in that kind of scenario what the root cause is. Or even if you can find, it'll take a lot of time and a lot of tribal knowledge to be able to isolate those issues quickly. Even then, there's the cause of human error, and it'll take a lot of time and effort, and nobody wants that. So that's where the cognitive AI engine comes in. It finds all of those alerts and it only shoots out the core alerts. It tells you what metrics or what alerts are the core ones, And if those are fixed, all of the correlated alerts or the sequential alerts which happen after that, it suppresses those, the secondary alerts, and you only have the main ones which require immediate fixing. When those main ones are fixed, your entire setup is fixed as well. You don't have to pay attention to those secondary alerts. So, with Cog AI, by creating sequences, you can send a war room alarm and give about maybe 5 to 10 minutes of a heads up to up to 30 minutes of a heads up, depending on how well the engine is trained on your data. And you can give that heads up way before the war room scenario occurs. So these alerts are suppressed, and you send out maybe two, three, four main alerts, and only those teams can get on call. All of the other alerts are suppressed, they're only secondary. And any teams which are required for those alerts or those services can spend their time not worrying about this issue, as they are not the cause of it. This leads to more productivity, more business efficiency, and can help more in more efficient spending and an increase in revenue as well. So, how does one improve upon this model? You can improve upon the model by providing more metrics. So, providing more metrics can give the model more context as to what's going on. Some metrics which may seem irrelevant to you and which you may believe are not necessarily required to isolate issues might actually be correlated in some way to some important crucial metric. And as humans, we may not be able to figure that out, or even if we are, it'll take a lot of time. Again, providing those additional metrics gives more context for the engine and increases the correlation between metrics and can help isolate issues faster. Another way to continuously improve and train the model is to give a search space. So, here by search space, we mean your application topology. But we don't just mean your applications, we mean your databases as well, your servers, your virtual machines, networks, anything which you can consider a part of your application estate, you can provide in the search space. This gives the AI more context on any application dependencies, any network dependencies, etc., and gives more context of the overall estate or the topology. This can help correlate, isolate, and come down to the root of issues much faster if the search space is provided. So, how does one improve upon this model? You can improve upon the model by providing more metrics. So, providing more metrics can give the model more context as to what's going on. Some metrics which may seem irrelevant to you and which you may believe are not necessarily required to isolate issues might actually be correlated in some way to some important crucial metric. And as humans, we may not be able to figure that out, or even if we are, it'll take a lot of time. Again, providing those additional metrics gives more context for the engine and increases the correlation between metrics and can help isolate issues faster. Another way to continuously improve and train the model is to give a search space. So, here by search space, we mean your application topology. But we don't just mean your applications, we mean your databases as well, your servers, your virtual machines, networks, anything which you can consider a part of your application estate, you can provide in the search space. This gives the AI more context on any application dependencies, any network dependencies, etc., and gives more context of the overall estate or the topology. This can help correlate, isolate, and come down to the root of issues much faster if the search space is provided. So, after continuously improving the model and continuously training the model on your application estate, on your services, networks, your correlated metrics, and any feedback that you as a user provide, here's an example of the proactive impact analysis for any future occurrences in your application estate. The scenario we'll be looking at here is for the symptom memory of a catalog service. So we're looking at a classic ecom setup. There's a deployment at 1 p.m. and the engine detects that there's a new deployment of the application or of the service, and the engine is on high alert. 5 minutes after the deployment, it starts to detect small spikes in some different metrics. 15 minutes later, at 1:20, it starts to see that the memory usage is increasing. So your catalog service is using up more memory than it normally did in previous deployments. And that's initially flagged as a symptom, but then it starts to become an issue. And because of this, the CPU usage starts to fluctuate as well. And that symptom leads to a degradation in the response time. So, just 22 minutes after a new service deployment, a new application deployment, your response time is going down, and your users will start to see issues and they might get frustrated if the response time degrades too much. Now, that response time degrading is a symptom of the core issue as well. Because of the response time degrading, the pods will crash and your catalog service is down. Because of that, the impact is also on a recommendation service connected to your catalog service. And because your recommendation service is down, your cart service is down as well, and your catalog service is also down. So because one deployment was changed, one deployment was faulty, you had the recommendation service go down, you had the cart service go down, and the catalog service go down. You had three services go down within 25 minutes because of some deployment change. With Cog AI, you would have been able to see the issues arise only 20 minutes after. So when the deployment is done, you start detecting small spikes, and even then you can see that something's going wrong. And when the memory usage starts to increase as well, you can prevent the issue before your services go down or before your response time degrades. So it gives you about a 5 to 10 minute heads up where your entire application estate might crash and fail, crash and burn before you can do anything about it. So finally, this is how we at Rakuten 6 Sense reimagine AI ops. We will auto discover the key performance indicators. We don't believe that the AI has to be manually told which indicators, which metrics are important and which are not. The AI can learn which are important by itself and start looking out for those by itself. It'll define the KPIs by itself. We don't want the AI to get validation on its thresholds by the SRE, and we want to get rid of suppression rules and correlation rules as well, along with CMDBs and fine tuning of the topology. We expect anomalies to be auto detected with zero discovery and configuration, nothing to be manually set up, no manual intervention at all. We want it all to be automatic. And the only manual intervention which we require, which, as we all know in most machine learning and AI cases, is the validation part, where the user validates an anomaly or a root cause. We only want the yes or a no. Yes, this was an anomaly. Yes, this was a root cause, or no, it was not. And if there are any root causes to be found, we will automate finding the root cause and give it to the user automatically to have a look at whether that was the root cause or not and what impact that might have had. With this, we expect to reduce application setup time by about 50%, and critical alert coverage we will cover by an increase in 90%. We expect war room scenarios to at least go down by 50%, although we do anticipate more, and for alerts noise to go down by 40%. So you can say goodbye to all of those alert storms. We also might integrate with auto remedy as well, and any advanced impact prediction is also a part of how we imagine AI ops to be. And with that, we finally come to an end to this webinar on alert storms and on war room scenarios and how Cog AI can help prevent those and help you and your team manage alert storms and war room scenarios much more efficiently, and how proactive impact analysis and instant RCA can effectively save you a lot of time, a lot of energy, and most definitely a lot of money. Thank you for tuning in. If you have any questions or feedback, please do leave that in the comments below. Once again, thanks for watching. Goodbye.